I plan for about an hour.
Yeah.
Might be slightly less.
So we're very pleased to welcome Jannis Bulian, who's come all the way from the north in Cambridge. But apparently he has some experience of London because he was at Imperial. Not an august institution like Middlesex, but we welcome people from Imperial nonetheless. Please.
Yeah, thank you. So I'm going to talk about the parameterized complexity of graph isomorphism. Mostly about some recent research I did with my supervisor, and which I want. First I'm going to say a bit about the graph isomorphism problem and a bit about its history. Then I'm going to give a very brief introduction to parameterized complexity. Don't worry if you haven't heard anything about parameterized complexity. It's I'm going to say everything that's necessary, and you can think of it as a very straightforward generalization of classical complexity theory. And then I'm going to say a bit about the research I did with my supervisor and so on. We introduced a new parameter and used that to study the parameterized complexity of sparse graphs. And in particular, we showed that the graph isomorphism problem is fixed parameter tractable, parameterized by a new parameter. So you probably are all familiar with the graph isomorphism problem. It's probably one of the most famous and well-known problems around. The question is basically given two graphs, are they isomorphic? So is there a bijection between that preserves the edge relation? Or, I guess in easier terms, can we just rename the edges of the vertices of one of them and then get the other one? What's interesting about this problem is that unlike most natural problems, it is in NP, but it's not known to be either in P or to be NP hard. So it's fairly easy to see that it's in NP. The isomorphism is basically a short certificate. But so far no one has managed to show that it's in P or NP hard. And that puts it in an interesting spot because if P is different from NP, then by Lagrange's theorem there should be lots of problems in that space. But so far graph isomorphism is really one of the few ones that are known and that are good candidates for that.
Was this? I think it was also it is also in these problems in the 70s, this list of Carr, that it says that it was not known whether it's NP hard or not, and probably it's only left, I guess. It is not known. Right? So,
I guess it's the most important decision problem whose complexity is open. So. And it's even worse because it's not known to be NP intersect co-NP or anything like that. It's
not likely to be there.
And it's not likely to be NP hard because then the polynomial hierarchy collapses.
Yeah,
there are all sorts of... It's an extremely unusual problem.
Yeah. So it might well be in theory.
Well, maybe we can touch on that already at the beginning of the talk. Do you believe it's in P?
It's hard to say.
So what's the implication if it is in P?
I think there are some implications that make it unlikely that it is NP hard, but I don't think I know anything that makes it unlikely.
well, I mean, there are problems not so well known which are equivalent to graph isomorphism, and in a sense there will be also PAS.
I think that's right, that it's
You can get things like this.
P is possible still. It's just no one.
Because what you said is true. I think there are a few problems.
There are a few problems, but not really, very, so not.
But I think they're not that well studied, and I think no one thinks that it's impossible that they
Yeah, that's what I mean, yeah.
I mean, the first person to prove it's in P, I'll buy them a cup of tea.
That's incentive right there.
It's very generous.
But is it P hard, for example?
What is it?
P hard.
I don't know, actually.
I'm not sure.
It's a good question.
You get another cup of tea.
Well,
By asking a kind of probably
it's
one question.
It's obvious that it's sort of been hard and speaking about
So,
at least that's how this has problems in P.
I'll learn the like log space reductions or something.
You mean the lower?
Lower reductions.
well, so anyway, that makes the problem quite interesting and quite unique. And there has been a lot of effort to push the boundary on like instances where it's where we can actually solve it in polynomial time. And this is basically part of that effort. So from the practical side, there has been lots of interest from mathematicians in combinatorics, graph theory, chemistry. I think it's one of them. It's quite important there because there's often a question if two molecules are structurally the same. And computer science, of course. I mean, it's one of the most important structures for computer scientists. And actually, in practice, it can often be solved quickly. I think the best program I currently know of is Norton. And for lots of practical instances, it actually works very fast. So that might point in a direction that it might actually be tractable.
Is that being solved by an exact algorithm?
Yeah, I think so.
So for planar graph it is in P. I mean,
Sorry?
for planar graph it's in P. So
Yeah.
there's no question.
Oh yeah, there are lots of.
It is.
There are a couple of graph classes where it's known to be,
Okay.
say, a bit more about
Okay.
it. So the problem has, of course, a really, really long history. It seems, I tried to find out when people first considered that problem, but it turns out it's not that easy to find good history of mathematics. So it definitely has been considered before the 70s and 80s, but that was a point when, after the initial ideas in complexity theory, people studied it really, really heavily, and tons of papers were published. Actually, so many that one of the surveys from Rita and Panel was titled The Graph Isomorphism Disease, because it attracted so many people and they made so little progress and wasted so much time. So the best known algorithm that came out of that time runs in time to do this very end.
Now, is n the number of vertices, or is it the size of the input?
The size of the input. And just to give you one example for graph isomorphism, are these two graphs isomorphic?
Take a vote on that?
Yes. Yes.
Do they have the same number of vertices? If they're yes, then yes, that's my first.
Yeah, I think it's not that obvious to see. With that labeling, you can see that they're actually isomorphic.
The Peterson graph.
Sorry?
The Peterson graph.
Yeah. And then, so next I'm going to say a bit about the framework of parameterized complexity. It's basically the answer to very general problem in computer science and of course engineering. Lots of problems are hard, are known to be NP hard, and still we need to solve them in practice. And there have been lots of different approaches to deal with this, like approximate algorithms, randomized computation, to well, introduce some trade-offs to still solve these problems. Parameterized complexity is a different approach because it actually helps to understand the problems better and still is useful in practice. The basic idea is that many NP-hard problems become easy if we just fix something as a constant. For example, for vertex cover, if we just fix the size of the vertex cover that we're looking for as a constant, we can just look at all the possible vertex covers and choose k and solve the whole problem and enter the k term. And that's the problem with that is usually that if the degree of the polynomial depends on that constant, then if that constant gets bigger, the polynomial gets bigger, and that quickly isn't feasible anymore. So what's even better is if we can find an algorithm that runs in time some function of the parameter times the polynomial. That's it. And the degree of the polynomial being independent of that parameter. Or more precise, it's basically the idea of a two-dimensional study of complexity theory. Instead of just looking at the runtime of an algorithm as a function of the size of the input, we look at the size of the input and some additional number that's somehow associated with the input. That can be the size of the output, or it can be something that has to do with the structure of the input. And there are lots of different ways to look at this. And if we get this, what I said before, some function of the parameter, this has to be any computable function, times a polynomial with a fixed degree, then the problem is called fixed point tractable. And FPT is the class of all the problems that are fixed point tractable. This basically gives us an approach to have a more fine-grained look at problems that are known to be NP hard or that are not known to be NP. And understand that complexity better. Just to give you an example of a problem, I mentioned before that vertex cover can be solved in time n to the k, which is all the k-size subsets, but that's not FPT because the degree of the polynomial depends on the parameter. But we can actually show this FPT with the following idea. It's actually quite easy. If we look at a graph, then every vertex that has degree larger than k, that has to be in a vertex cover. Because otherwise you would be allowed to only include at most k vertices in the vertex cover, and that can remove at most k edges, so there would still be edges left. So we know that we can take all those out, and for each of them we reduce the number of k value. So we can keep doing this until the degree of the graph is bounded by k. And then we can make the observation that if there are still more than k squared edges left, then there can't be a vertex cover. Because each vertex can now cover at most k other vertices, k edges. So k vertices can cover at most k squared edges. And if there are more, then there are edges that can't be covered.
You need to remove isolated vertices as well.
Yeah.
But yeah, you can assume they're not there.
You do.
It's trivial.
We assume that they're not there.
Yeah.
Oh yeah, assume they are there. Yeah. I mean, you can always do that for vertex cover. And otherwise, the graph is actually quite small. It has at most 2 k squared vertices, because we have at most k squared edges. So in the worst case, the graph is basically the graph of the x of vertices that have an edge between them. So, and that's just bounded in the size of the parameters. We can just brute force solution. And 2 squared, choose k, and that's just in terms of the parameter. So that problem is fixed point tractable. So in this example, we looked at the parameters, basically the size of the output is the size of the vertex cover we're looking for. Another way of looking at it is looking at structural parameters. Parameters that say something about the structure of the input. For example, parameters like the maximum degree of a graph, or the tree width or tree depth of the graph, or the genus of the graph. That basically leads us into understanding how certain structural things make problems easier to solve. And actually, for graph isomorphism, we know that on lots of different classes of sparse graphs, graph isomorphism becomes easy, or polynomial time solvable. That was part of the effort in the 70s and 80s, although that led to results like graphs upon the genus can be solved in polynomial time. bounded degree was shown below, which is the problem I was talking about, the best known one. And a bit later, there's an algorithm by Bulian that shows that graphs of bounded tree width can be certain for normal time. And also the size of the small is excluded minor. However,
but from these papers from the 80s and from the 80s, it was not, I mean, they didn't, so was the genus, for example, was the polynomial independent of the genus, or they didn't say it, or, because still, I mean, you can say it for a long time, but, so.
basically treating the genus as a constant.
Treat the genus as a constant, but it was not n to the genus, it was some constant times the polynomial n. That's what
But I think it was bounded by n to the genus, right? I mean, it wasn't exactly that.
Yeah, but the slide seems to suggest that it was putting it in XP, not FBT. You think it was actually already putting it in FBT?
So when I looked into this some years ago, it seems that some people using some maybe non-constructive proofs, they were showing that, well, the problem is actually, they were actually showing the problem is FBT, that was in the 80s, but they were not showing what is the dependence. Or they were showing, so either they were showing n to the genus, or they were showing function of genus times something, but they didn't say what the function is, or they didn't even look at that somehow.
Okay.
So I just don't know about the genus itself, basically. That's the,
Do you recognise those authors? Was it those authors that you were looking at? I can't remember.
I can't remember. I mean, the first shows actually that for planar graphs, the genus is 0 for planar graphs is actually for a long time anyway. So,
right, that's a good point. So is what for genus 1, do we already get NP hard? And
I don't know, but let me continue that because we'll never finish.
Yeah, so as you said, these results basically show the runtime n to the k, or as you said, that those problems are in XP. But the interesting question is, are they actually? Well, the question I was doing is, where is it actually FBT? So there have been, later than in the 90s or 90s, results on FBT of structural parameters. In 97 it was shown that it's FBT parameterized by tree distance width. Then something as obscure as the maximum size of a simplifiable component and largest multiplicity of an eigenvalue of the adjacency matrix. Yeah, I think that's when the linear algebra approach became a bit more trendy to graph theory. The size of the feedback vertex set, which is basically the number of vertices we have to delete so that it's a forest, or to hit all these equals. And then quite recently it was shown that it's parameterized by tree length. This is FBT. And just this year it was shown that it is actually FBT parameterized by tree width, which was quite a big result. I think what people have tried to get that for quite a while. And actually our research was initially also motivated by getting there, and then we diverged.
And what's the relation, possible relation between these parameters? For example, this third one, the largest multiplicity of the eigenvalue of the and the tree width. So what's the relation?
So for most of them, I don't know about the relation. I'm not quite sure if there's actually a relation. Tree width is a generalization of tree depth. And what the parameter we looked at is actually now a parameterization of tree depth that's incomparable to tree width.
If they are, in this order of publication, if the papers are, and I think from the authors they're reasonable papers, probably there is no connection, because if there was a clear connection, and if you show that it's FBT with one parameter, and the other parameter is always bounded by the first one in some sense, then it's FBT for the other one as well, so there's nothing to show, but probably they're independent in a sense.
Oh, it could be the other way. It could be the other way.
Yeah, and I mean these look at graphs in very, very different ways. So
have you read this last result of tree width? Is it complicated?
Well,
it is a bit complicated, yeah. It basically takes Bulian's algorithm and makes it work in the parameterized framework by adding a couple of very clever ideas.
You have to give it the tree decomposition, don't you? It doesn't calculate the tree decomposition.
Well, but even if you did, it wouldn't matter.
I think it works similar to Bulian's algorithm.
Because calculating a tree decomposition...
No, it's FPT.
Yeah. It's FPT, okay.
It is.
So it doesn't really...
Yes, FPT by first computing a non-optimal one, and then from there you
And then,
can
yeah,
clear the
it's
optimal one.
Bulian's algorithm.
Yeah. And so the parameter we have then looked at comes from the framework of something called distance to triviality. It's a general approach that's used in fixed mode attractability, algorithmics, or parameterized complexity. The idea is basically to come up with some kind of measure that measures how far something is away from being trivial. Where trivial means that we know a polynomial algorithm is solved. And then use that as a parameter and see if it becomes fixed mode attractable. So for example, tree width is a way to look at distance to the graph being a tree or a forest. And feedback vertex set is that tree. For true, in very different ways. Tree width basically, if something is a thick tree, well, feedback vertex set is just, is there a number of vertices that we can delete so that it's a tree? And another example is vertex cover number, which basically just measures how many vertices we have to delete until the graph doesn't have any edges left, which of course makes most problems very easy to solve. The notion of triviality that we use for graph isomorphism is bounded degree, because Lux showed in the 80s that if the degree is bounded by a constant, then we can solve the problem in polynomial time. So we look at distances to graphs that have degree bounded by some constant. First, we looked at deletion distance to bounded degree, which is basically just, is there a number of vertices? If we delete those, then we have a bounded degree graph. And a graph has deletion distance k degree d if there is vertices we want to be k, and if we take them out of the graph has degree d. Calling that set with d deletions. So first I'll show that deciding if a graph has deletion distance k to bounded degree is actually FPT. So it works in a similar argument to the vertex cover argument. The first observation is that all vertices of degree greater than k plus d this time must actually be contained in a d-deletion set. Because otherwise, if we delete k vertices and the degree was greater than k plus d, the vertex is still degree greater than d, so it has to be in there. So we can remove all of those this time, and for each of them reduce k by 1. And then we define a set U of the interesting vertices, basically. All the remaining vertices that have degree greater than d, or a neighbor that has degree greater than d. And that means that this set U of vertices must contain all the d-deletion sets of minimal size. Also, if U has at least size k plus k plus k plus d plus k plus k plus d squared, which basically means that we can reach vertices in 2 steps in the graph bounded by degree k plus d with a set of size k. Then there cannot be a deletion set, because that means we can't reach everything we need to reach with these deletions. So that means we now have, again, a size of, this is basically what's often called the computational complexity of the kernel, the core of the problem. So we can just solve the problem for U now. The size of U is, again, just bounded in terms of k and d and k plus d. So we can solve the problem in a function by just say brute forcing in a function of k and d. But this as u can actually also be used to test for graph isomorphism of graphs that have deletion distance k to d. So, I mean, as I said before, the set U contains all the vertices of degree d and all the vertices with a neighbor that has degree at least d. So given two graphs, G and G prime, say, we can compute these sets U and U prime for both of them. Then we just, because these have bounded signs, we can just enumerate all the isomorphisms between the sets U and iterate over each isomorphism vectors that we can find. For each of them, we can color the vertices outside of U by basically just taking the set of neighbors and
the degree.
No. Sorry.
The degree of the vertices, or and then the set of their neighbors.
No, just the set of the labels, because the sets U and U prime are small. We can basically just enumerate them using the same enumeration that is preserved by the isomorphism.
Okay, yeah.
And then we get a coloring that gives us exactly how everything is connected to something in the set U from outside the set of U. And then basically we just have colored isomorphism on bounded degree graphs. And that can be solved by Luke's algorithm. Does that make sense? So this was the first parameter we looked at, and then we looked at another one. If C is a class of graphs, we're interested, we define something called the elimination distance to triviality, or the elimination distance to that class C. The idea is to generalize the idea of deletion distance to something that's similar to tree depth, by not just deleting vertices one after another, but by allowing to delete a vertex from every connected component of the graph, and doing that repeatedly.
Sorry, can you say this again? I'm not sure I get
So the idea is basically to recursively delete a vertex from every connected component.
So you can delete them in parallel from different components, essentially.
Yeah. So essentially you can think of that as a bit of a parallel computation by treating each connected component separately.
Okay. And then the parameter is
basically the number of deletions,
the number of
steps you allow.
The number of steps, but do you how many deletions you actually do in step?
Depends on the number of connected components.
Lots of components. No, you don't count that. So
you don't count. Okay.
So if you manage to split up the graph into lots of
some components, I see.
You might delete an unbounded number.
I see. Okay.
Or more formally, the elimination distance to the class C is 0 if the graph is actually already in C. It's 1 plus the minimum of the elimination distance to G minus V for all the vertices V if the graph is connected. So we delete the vertex from a connected component that minimizes the elimination distance. And it's the maximum of all the components in the graph if the graph is not connected. And if you know tree depth, that definition might actually look quite familiar. So tree depth basically generalizes, it's a generalization of tree depth where basically if you choose this class C to be just the empty class or the empty graph, then you get tree depth. Another way of looking at tree depth is as a rooted via tree depth decompositions. The tree depth decomposition of the graph is basically a tree routed directed tree that has the same vertices as the graph and contains the graph in its symmetric transitive closure, which essentially means that whenever we have an edge in the graph, we need a path in the tree between the two vertices. And then the tree depth is just the minimum height of all the tree depth decompositions. Here are a few examples. The first one is a K4, and because everything is connected to everything, the tree actually has to be a path. Because it has to be contained in the symmetric transitive closure. The K33 looks a bit more complicated. So the tree depth decompositions are in yellow on top of that. So black is the original graph, and the tree depth decompositions are in yellow. Is yellow visible? Yeah. And for a path, we can actually see this basically recursive structure. That taking the first one is basically like cutting it in two parts, and then we get two paths of each of length 3, and we can take out the vertex again, cutting them in half. And
so actually, it's what you're saying here is something that is not written much in the literature, but tree depth is actually the same as point width. So if you have tree width, path width, point width. Point width, it actually appears in Downey Fellowes' first book, and it somewhere comes from Robertson Seymour in one of their early graph minors papers. But about what you're saying about tree depth being removal to an empty graph, what you're saying is tree depth is the graphs are point-like. Just like bounded path width for path like a bounded tree width for tree width. But it's not noted much, it's in Downey Fellowes, but it's not noted much else in the literature. I once wrote to Nestratil about it.
Yeah, it's true. Yeah. It's basically the way you get a tree width decomposition or path decomposition from it.
Yeah.
It actually gives you a point decomposition. Yeah. By just taking all the branches. Yeah, that's an interesting way to look at it.
And so there's also the parameters. So there's a related parameter here, tree depth.
Yeah, so tree depth is related in the following way. That if we have elimination distance or k to some class of graph C, then this actually means that there is a subgraph with a tree depth decomposition, which has height bounded by k. And all the remaining components of the graph, if we delete that, are in the class C. And each of them is connected to at most one branch of that. So it wouldn't be allowed that this is connected to the other. So one can think a bit about this as a tree depth decomposition through these are the leaves. And the leaves are in subclass. So our notion of triviality is bounded degree graphs. So this class C that we look at the elimination distance tree, we choose to be graphs bounded by degree D. So that the definition becomes this. And this is basically what changes if the maximum degree of the graph is bounded by D, the elimination distance is 0. So the relation to other parameters is so basically if for a graph we have that the elimination distance it's bounded above by the deletion distance, of course, because basically the deletion distance is value of the path. And it's bounded both by the tree depth, because the tree depth is just the empty class. It's also an interesting observation, I guess, that if a class has bounded expansion, and then the class with bounded elimination distance to that class also has bounded expansion.
This bounded expansion is something introduced by Nestratil and Asano de Mendes, and it's quite It's got a complicated definition over K-shallow minors and things. It's kind of, the definition looks kind of weird, but actually it's very natural. Actually, I just bought that book of theirs and we'll dive into it, but it's...
I will read it later.
Yeah, so I think this only makes sense if you know what bonded expansion is. And I don't think there's a point of explaining what it is.
No, it's quite,
It's a notion for sparsity of a graph that's quite general and includes lots of different other classes of graphs. And
yeah, it's a very natural notion of sparsity, actually. It's meant to generalize a lot of other... Yeah, that's a good description.
So the main question was, given nowadays graphs of elimination distance k to some degree d, how can we actually test for graph isomorphism? So I guess the naive idea would be just to compute an elimination tree for both of them and then compare. But of course, if we have two isomorphic graphs, they might actually give us completely different elimination trees. And so we would need to find something that's actually canonical, and we didn't quite know how to do that. And also, we don't even know if it's FPT to find the elimination trees. And we still don't. So we need something that's invariant in isomorphism, and we need to do something that we can actually do in fixed parameter time. So the first idea then is to compute. Basically the first idea is to just look at high degree parts of each graph and compare them, because they are invariant in isomorphism. Right? We just take everything that has, say, a degree higher than d, compute a tree, depth decomposition of that, and do the same for the other. However, although, that gives us something where the components that are outside of that tree have degree bounded by d, but unfortunately we also need to meet another condition. Basically, these components might be connected to more than just one branch of this tree, and we don't really know how to bound the tree depth of that tree if we compute it. So in pictures, we have the problem that if this is just all the vertices of degree larger than d, and we compute an optimal tree depth decomposition of that, we don't actually know what the height of that is going to be, because just because it has elimination distance k to degree d doesn't mean that this has to be shallow in some way. And also, there's no guarantee that this is connected to just one branch. It might be connected to several branches and violate the condition. So, to deal with that problem, we introduce a new notion that we call the d-degree torso of the graph. It's basically taking all the vertices of degree larger than d and taking the supergraph of that by adding an edge between two vertices if there's a path through the lower degree part of the graph. So we add an edge whenever we can reach one from the other through the low degree part. And using that, we actually managed to prove the following. If a graph has bounded elimination distance k to degree d, and we compute this d-degree torso, then computing a minimal tree depth decomposition of that d-degree torso gives us actually an elimination tree. And that elimination tree's height is bounded by that function, which only contains k and d, so it's good.
So now, this will end up also exploding in the runtime somehow, right?
Oh yeah, it might not be the most practical.
Yeah,
but it's certainly computable.
It's even elementary. and that's an elementary function. So.
So we have both properties that we need now. We have this is bounded by a function of k and d, or treating just d as a constant function of k. And each of these components is now connected to just one branch.
Something I'm maybe missing, but the number of different ways you can have this diagram, this tree depth decomposition, is bound by f of k. Right? All the different. So you said there isn't a canonical one. There isn't just one doing it. Well, I can't.
Oh, there might be arbitrary branching.
But why can't you test them all? Because the number of them is f of kd.
Oh no, that's the height.
Okay.
I mean, the number of leaves might be unknown.
Ah, okay.
But if we have both, that's true. Then we can just do it.
I see.
So how does that help with solving graph isomorphism problem? First of all, the first important observation, I guess, is that these d-degree torsors, the way they are defined, they are invariable in isomorphism. So if we have two isomorphic graphs, we will end up with the same d-degree torsors. Because it's really just taking the parts that have high degree and connecting vertices that have a path through the part of the graph that is lower degree, and that's the same for two isomorphic graphs. Then we end up with these tree depth decompositions of the d-degree torsors, which and the paper by Bulian and others shows the canonical way to find tree depth decompositions. And so we use that algorithm to take that canonical part of the graph and compute again the canonical tree depth decomposition. And then we can just use this canonical tree depth decomposition that we have on top to label the vertices in the lower degree part. Because each of those has at most that function of k and d neighbors on top. We end up with basically a feasible label for those. And then again, Baba and Hooks have this canonization algorithm for bounded degree graphs, so we can assign a canonical form to each of these colored components that we have at the bottom. And so we have a label, we end up having a label tree, and we do that by attaching two labels to each vertex in the tree. The first is basically just to preserve the structure. If we have a vertex in the tree, we just say which things it is connected to on top. And the second is the canonical forms of the degree components. If we label them, then we basically have all the information that, that's in the original graph captured in that canonical form. And since this is then just a label tree, we can use Rundell's algorithm to actually solve, to either come up with a canonical version of this or compare the two. Yeah, so that's essentially how we do that. There are a couple of...
So you said
was that
in the beginning you said that you were actually aiming, or originally you wanted to tap the tree width as a parameter, but then you ended up doing this. But so when did you realize that this will not actually give you something, because it's not really clear how it's going to?
Oh, really?
How would this kind of be connected, or how?
Oh, yeah, we realized quite quickly that this is incomparable to tree width.
Okay.
But we thought this was actually quite interesting in itself.
Yeah, of course.
And I think it's also a very natural generalization of this idea of deletion distance. And yeah. So yeah, so there might actually be other problems that are now FPT parameterized by this new parameter. And well, we haven't found any yet, but I think it might be worth looking into. And this parameter, elimination distance to triviality, might be useful elsewhere too. It's as I said, I think it's a very natural generalization of deletion distance. Deletion distance has been studied quite a lot in the area of parameterized complexity. And this elimination distance might give us even more wider classes of tractable classes for lots of problems. For graph isomorphism in particular, elimination distance to bounded genus or graphs excluding with fixed minor might be interesting. And we looked a little bit into that for the bounded genus, or just even something as simple as elimination distance to planar graphs. And the idea is that we don't generalize that easily, so I think if someone would attack that, they would need to come up with new methods. But it looks promising.
So going back to my original comment, so for when genus is a parameter, it is FPT. Right? It's known that it's FPT when genus is a parameter. Or not? I don't remember actually this.
I think it should be on that slide.
Not here. It was on the previous one.
Oh yeah, but that was for
it's an XP, wasn't it?
Yeah.
So we should look it up, right? Let's look it up.
I don't think it is.
Let's see if we can find it afterwards.
But yeah.
Okay.
We'll have a look at something.
Okay.
I
See
don't
if we
think
can
it
find
is.
out.
But I might just move on. Yeah, so I think it might be worth looking at it a bit more, and we're doing that. At the moment, we're trying to find out if actually deciding if a graph, if elimination distance to bounded degree is actually FPT, deciding if a class of graphs has elimination distance k to bounded degree. Well, okay, to summarize. So we introduced this new structural graph parameter, elimination distance to bounded degree. We showed that graph isomorphism is FPT, parameterized by this parameter. And I think this opens, well, basically a new class of graphs to look at and see if problems are FPT parameterized by this distance to triviality.
Okay, thanks very much. What about elimination distance to graph on graph holomorphism now instead of isomorphism? So holomorphism, which is an NP-complete problem, it's what would happen there? So it's obviously it's W1 hard when the parameter is the size of the left-hand structure of the homomorphism. But if it's not the size that's the parameter, but now some elimination degree, something could. No, it should still be W1 hard, though, shouldn't it? Which is the.
I'm not entirely sure. I mean, it's a much harder problem.
It should still be W1 hard.
Yeah, I mean, it's definitely.
If it's W1 hard, even with the size of the input, then these parameters are smaller, so it's still W1 hard. Any more sensible questions?
I have a very non-sensible. When we move to that non-sensible category.
Yeah.
Rather sensible. Okay. So I'm very ignorant about the area, but I have a sort of a general purpose question. Is it true that the algebra isomorphism problem is reducible to the graph isomorphism problem? Let's say for arbitrary signatures with function symbols and relation symbols. Because this is the establishing isomorphisms of universal algebra is an interesting problem in itself.
Yes, it is. You can code any structure for isomorphism with a graph. You can't do it for homomorphism, but for isomorphism definitely you can. Yeah. So graph isomorphism is as hard as the general structural isomorphism problem.
Oh, okay. So then are there any results for like equational classes of algebras? I don't know, like groups? I would assume that this is an interesting problem. You probably can optimize.
There must be, right? But I can't bring anything to mind. There must be some.
And then the question is whether this approach would actually influence if you switch to this from this problem to the problem of isomorphism of algebras. Would this make? I mean, of course, the problem is irreducible, but then the actual techniques that you use here are they also transport?
Even how they would translate back to?
Yeah.
I'm not sure. It seems
because they seem quite graph specific.
Do you know the complexity of group isomorphism? Do you know anything about it?
Group
isomorphism? Group isomorphism. Finite group isomorphism. Well, again, something we should look up.
Well,
it must have been studied. Maybe it's equivalent to graph isomorphism already that you can code anything into a group.
But then I think the next question is there a corresponding thing as elimination distance to reality?
Yes, because they are quite specific. They seem quite specific graphs, but probably they generalize.
Yeah, I'm not sure how it would translate to groups. It's an interesting question.
Yeah, personally, I care less about groups and more about general structures.
No, but you could do like the distance to abelianness or something, or the distance to. There must be group parameters you could do.
Is this kind of problem interesting? I mean, you can introduce many such parameters. Let's say it's okay. You have a group. Then you say, okay, what's distance? So you probably have to add some generator or delete some generator. Then it becomes abelian. Okay, I mean, what's
so
the
you
point?
could say that the parameter would be for abelian by finite groups, it would be the index of that. So that would make sense as a parameter.
Yeah, because groups are much more connected than graphs.
Right.
They are connected no locally connected, so to speak.
So how much more structure to work with?
So how about like subgraph isomorphism? Well, it's MP hard.
That's a much harder problem.
But I mean, can you like study?
That's a much easier. That's a harder problem. Well, with respect to complexity, but easier with respect to getting results.
Yeah,
so it's known it's MP hard, and I think
it would be W1. I mean, it will already be for these problems will not be FBT. I think.
No. Right. So subgraph isomorphism is FBT with respect to many parameters.
Yeah,
not
you can't
with respect to the size of the left-hand structure, even, because that's the complete problem. And these parameters are smaller than that, so it should.
I think. No, I'm talking about general parameters. I'm talking about the general parameters. I'm talking about tree width and other parameters. I think it's FBT which will be from
I see, because you also got the right hand there. Maybe you're right.
Could you write the structure of which graph?
Well, it both graphs also bound to, for example. I think it was known before this, the graph isomorphism itself, or other parameters, but I might be mistaken.
Yeah, I'm not sure.
Oh, if there are no more questions, then perhaps we can thank Jannis. Are you able to stay for a bit this afternoon?
Yeah, sure.
Maybe we will go to the pub.